The quark-gluon plasma created during heavy ion collisions exists for an incredibly brief moment, just around 10 to the power of -23 seconds, making it impossible for physicists to observe directly. To learn more about this elusive state of matter, researchers instead analyze the particles that emerge from the collisions and pass through the plasma, revealing crucial information about its characteristics. At CERN's Large Hadron Collider, LHC, researchers have uncovered the crucial role of the top quark in advancing our understanding of quark-gluon plasma, the extremely hot, dense state of matter thought to have existed just moments after the Big Bang. The top quark stands out as the heaviest elementary particle discovered so far, significantly outweighing all other types of quarks. What makes the top quark particularly valuable in these studies is its incredibly rapid decay process. Scientists explain that the top quark decays into a W boson and a bottom quark so swiftly that this happens even before the quark-gluon plasma has fully formed. Specifically, the top quark's lifespan is so brief that the plasma cannot influence it directly. Instead, the decay products of the W boson start interacting with the plasma only after it begins to form. This precise timing acts like a natural stopwatch for physicists, enabling them to measure and track how the quark-gluon plasma evolves and changes over time. By analyzing these interactions, scientists gain vital insights into the behavior and properties of this primordial state of matter, shedding light on conditions that shaped the early universe. To provide a quick clarification, the bottom quark ranks as the second heaviest among all 6 quark types. Meanwhile, the W boson, along with its counterpart, the Z boson, is a fundamental particle that mediates the weak nuclear force. This force is crucial in processes like beta decay, where it enables certain types of radioactive transformations. With this foundation in mind, let's delve into the latest findings from CERN. Scientists working with the ATLAS detector at the Large Hadron Collider, LHC, the same instrument that played a key role in the groundbreaking discovery of the Higgs boson, focused their recent research on high-energy collisions involving lead ions. These collisions occurred at an energy of 5.02 teraelectronvolts (TeV) per nucleon pair, taking place over several years from 2015 to 2018. In this complex environment, researchers detected the production of top quarks by analyzing what is known as the lepton decay channel. In this process, each top quark decays into 2 particles, a bottom quark and a W boson. The W boson itself doesn't last long and further decays into either an electron or a muon, accompanied by its corresponding neutrino. This detailed chain of particle transformations provides crucial insights into the behavior of fundamental particles under extreme conditions, helping physicists test the predictions of the Standard Model with greater precision. The result once again shows a statistical significance of 5.0 standard deviations, marking the first ever observation of top quark pairs produced in heavy ion collisions. The team behind the discovery highlighted its groundbreaking nature, stating, "We're especially proud that our analysis does not rely on identifying bottom quarks in these events. This opens the door to using our method in future efforts to calibrate bottom tagging in heavy ion collisions, a notoriously challenging task that's essential for studying the time evolution of quark-gluon plasma." In summary, the ATLAS team measured the top quark production rate with a relative uncertainty of 31%, primarily due to the limited size of the current dataset. However, future heavy ion runs are expected to improve this precision significantly. In fact, the researchers are already working on follow-up measurements that will explore how a top quark decays into 2 other quarks. This breakthrough will enable scientists to better understand the fundamental nature of the early universe more accurately than ever before. Take, for instance, the strongest magnetic field ever detected in the cosmos. It offers a window into the conditions of the universe mere moments after its birth, conditions so extreme that calling them intense would be an understatement. Just 10 microseconds after the Big Bang, the universe existed as a quark-gluon plasma, a superhot, ultra-dense state of matter. At this stage, particles were packed so tightly that the density was up to 10 times greater than that of an atomic nucleus. Temperatures soared above 2 trillion degrees Celsius, hotter than the core of any star. Under these extraordinary conditions, particles in the plasma moved rapidly and interacted intensely. But what's truly fascinating is its behavior. Despite being made of what we usually think of as hard particles, quark-gluon plasma flows like a liquid. In fact, it's considered the most perfect fluid known. So fluid, it exhibits virtually no internal friction, allowing it to spin faster than any other known substance. So how did the universe move on from this exotic state? The answer lies in a process called hadronization, which transformed this primordial plasma into the matter we know today. This suggests that elementary particles emerged directly from the primordial soup, a superheated, ultra-dense state of matter that existed just moments after the Big Bang. While scientists are still piecing together the exact mechanisms behind this transformation, what we do know is that this chaotic mixture of particles eventually cooled and evolved, giving rise to the structured cosmos we see today, from galaxies and stars to planets and life itself. Recently, researchers from the Star Collaboration made a remarkable breakthrough in our understanding of this early phase of the universe. In an effort to explore the mysteries of the primordial soup more deeply, they managed to generate what is likely the most powerful magnetic field ever created by humans, perhaps even in the entire universe. But let's rewind a bit. To conduct their experiment, the team turned to the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory in the United States. Using this cutting-edge facility, they accelerated atomic nuclei, specifically of gold, ruthenium, and zirconium, to near-light speeds and smashed them together at energies reaching up to 200 gigaelectron volts, GeV. These high-energy collisions recreate the extreme conditions of the early universe for a fleeting moment, lasting only about 100 quadrillionths of a second, producing a state of matter known as quark-gluon plasma. Interestingly, not all of these collisions are perfectly head-on. In many cases, the ions strike each other slightly off-center. These asymmetric collisions not only create quark-gluon plasma but also generate immense magnetic fields so intense they allow physicists to probe the deepest laws of nature that govern the birth of the universe. When heavy ions collide at near-light speeds, they create an intensely energetic environment. The result is a swirling cloud of subatomic particles and plasma. Within this maelstrom, quarks, gluons, and positively charged protons, many of which have not yet decayed, begin to whirl and rush past one another. According to theoretical predictions, such chaotic motion should generate an extremely powerful magnetic field. However, for a long time, scientists lacked concrete evidence about just how strong that magnetic field truly is, or how it influences the exotic state of matter known as quark-gluon plasma. That uncertainty has now been resolved. Researchers working with the STAR experiment at the Relativistic Heavy Ion Collider, RHIC, have made a groundbreaking discovery. They found that these high-energy collisions generate a magnetic field with an astonishing strength of 10^1 Gauss, that's 1 quintillion Gauss, or 1 trillion times stronger than a typical refrigerator magnet. To give you a clearer picture, Earth's magnetic field is only about 0.5 Gauss, and even the strongest man-made magnets barely reach 100,000 Gauss. This newly measured field is likely the most powerful magnetic field ever observed in the known universe. Even neutron stars, some of the most powerful magnetic objects in the universe, pale in comparison to the magnetic field generated by scientists inside a particle accelerator. The researchers managed to create a magnetic field roughly 1,000 times stronger than those found on neutron stars, pushing the boundaries of what was previously thought possible. This intense magnetic field was applied to a swirling cloud of quarks and gluons, the fundamental particles that make up protons and neutrons.